Okay, I guess we're live. So welcome everybody to our first keynote. The theme of these keynotes is interesting things to do with FPGAs. So I'd like to introduce our speaker, Phil Harris. Phil received his BS in physics at Caltech and PhD in physics at MIT. His thesis was on the first data from the Large Hadron Collider, the LHC, at CERN. As a postdoc at CERN, he played a leading role in the discovery of the Higgs boson. As a staff scientist at CERN, he led the effort to search for dark matter at the CMS experiment on the LHC. As a professor at MIT, Phil is working on deep learning strategies to measure the Higgs boson and dark matter, and he has helped to build the fast machine learning community aimed at deploying real-time machine learning in the broader physics community. Phil, welcome to FPGA.
Thanks, Paul, and thanks to the organizers for inviting me. So I'm going to talk today mostly about my research on the Large Hadron Collider. So here is the Large Hadron Collider. This is in Switzerland, Geneva, Switzerland. And it's a large underground ring. To put in scale how big it is, this is the Geneva International Airport where you can land an A380 Airbus. So it's a large international runway. And circumference around this device is about 25 kilometers. So it's quite long. And if you look at these points here, these are where they're specific particle detectors. And if you go underground 100 meters, you'll see a detector that looks like this. There's actually 4 of these. And there's kind of 2 main all-purpose experiments. So this is the one I work on, the compact muon solenoid, or CMS experiment. And then there's another one called the Atlas experiment, which is, in fact, even larger than this one. And so what do we do? Well, the LHC is actually, it only does one experiment. And the experiment is to just take a proton, accelerate it to really high energy, take another proton, also accelerate it to the same high energy, and then collide them. And that's the only experiment we do. We just collide 2 protons on each other, and that's it. Well, why are we trying to do this? Well, what we want to do is we want to recreate energy densities that are high as, let's say, the energy densities in the early universe. Right? If you look at the energy density, in space right now, it's very small, right? It's cold out there. But as the universe was smaller and smaller and smaller, it got to the point where the universe was quite small, and the energy density within the universe was really large. And what was happening was all sorts of new particles and forces were interacting to help produce the matter that we see in our universe today. And so what we do at the LHC is we try to recreate these energy densities and look at the particle interactions and try to understand them. How do we do this? Well, we use these big detectors, and these big detectors have various different detector technologies. So here's the CMS, a slice of the CMS detector, and we have kind of 4 main detector technologies. So in the inner detector, we actually have, it's kind of like a CCD camera that takes photos, and you get hits, and then you can connect the dots, make a track for charged particles. You have something, this green thing and this orange thing, these are calorimeters. So they measure the energy deposits. So if an electron, for example, goes into the calorimeter, you can measure the energy of an electron. And then, these large detectors on the outside are actually for measuring muons, which are like a heavy type of electron. Well, what we do is we go from detector hits to particles, and then we go from particles to collections of particles to actually find the fundamental particles. And what we actually probe at the LHC are not just the particles from the decay. We actually probe let's say the original particles that decayed into these particles. So for example, you can have a Higgs boson decaying to electrons and muons, and then you can take the electrons and muons and reconstruct the original Higgs boson and understand its properties. And in the end, right, there's only actually 13 fundamental particles that we know of in the universe. And these are fundamentally what we're looking at all the time at the LHC. So here's a very simple collision. This is one of the first collisions we ever had. you can kind of see how we do our reconstruction. We have these hits, we have energy deposits, and you end up with a bunch of different particles flying out. And you can look at the properties of these particles to understand what the physics is going on. And what we do, what we run is, we just constantly are taking data, same experiment over all the time, and we just look at it, try to see if there's something interesting. Here's an interesting event, and here's kind of a more modern event. You could see the first event I showed you was kind of simple. Now you see there are a lot more charged particles, and the event display is nicer too. And actually, any high-energy physicist would see this event and know right away what it is. They'd see a muon here, and then actually these two green guys are electrons. And so 2 muons and 2 electrons. This is actually a very likely signature that it's probably a Higgs boson. In fact, a Higgs boson that decay to Z bosons that then decay to these particles. Now, we only do collide protons on protons. So how do we get all these interesting particles? Well, it turns out that to get interesting particles, there's always a low probability of this happening with time. So if you have a single collision, right, then let's say your probability is 1. But you say 1 in a million collisions, you'll have something like this, which is a W boson. This is a weak boson. It's the particle that's actually responsible for the weak nuclear force. So if you're familiar with beta decay, this is actually the fundamental force particle that causes that. And this happens about 1 in a million collisions. The neutral electroweak boson, the so-called Z boson, is a little bit lower rate. And then if you look at the kind of 1 in a billion range, you start to see interesting things like top quark pair production. You also see eventually kind of pairs of boson production. And eventually you see the Higgs boson here at around 1 in a billion collisions. And so the idea is we just collide, and we collide as much as we can, and we try to see interesting collisions. So how do we collide as much as we can? Well, along this whole 25-kilometer ring, we have bunches of protons that are spaced along the ring, and they're spaced 25 nanoseconds apart. So what does this mean? It means we're going to collide at 40 megahertz. So every 25 nanoseconds, we have a new collision. Now, you can start to think about kind of the data you have. With all these detectors, a typical event is about 8 megabits. And so if you're colliding at 40 megahertz, you're talking about a data rate that's about 320 terabits per second, right? And so you want to be able to process this data rate, process each collision with an initiation interval of 25 nanoseconds. Now, I said we just collide 1 proton at a time. That was the case when we started the LHC. But these days, we want to increase the intensity of the beam as much as possible. So we actually collide, we make the bunches of protons dense enough so that on average, you get as many as 70 collisions at the same time. Now, since we're looking for collisions that happen 1 in a million, 1 in a billion times, of the 70 collisions, we're only really interested in 1. And so we need to come up with strategies to kind of isolate the 1 collision we care about and downweight the other collisions. Now, as a note, we're always upgrading our accelerator. And so at the moment, we do 70 overlapping collisions. But in the future, we'll do as many as 200 overlapping collisions. So it's going to be a very complex process to disentangle all of these different collisions and find the 1 collision you're interested in. Well, despite all of these complications and these large data rates, we've made a few discoveries in the past 10 years. You're probably all familiar with the Higgs boson discovery, which is now almost 9 years old, and it won the Nobel Prize. The discovery led to the Nobel Prize in 2013. Well, how does a discovery look like? So here's one of the actual plots we made for the Higgs boson discovery. And so what we do here is we select 2 photons in our event. We take the photons, we combine them, and we can take a relativistic invariant mass. And then we just look for a bump. And as you accumulate data over time, you'll suddenly see that there starts to be a bump in your data. So you need to take a lot of data, you need to look at a lot of collisions, and you look at a specific topology to try to find a signature. And so that's how particle physics works. Trying to look for bumps in the data and trying to see if there's something you just don't predict that's not there. Well, what are we looking for now? I mean, we discovered the Higgs boson, And what we've done is we've continued to analyze the Higgs boson. We still don't know a lot about it, but we've learned a lot in the past 10 years. But we're also doing other searches. So here's actually a collision that looks like dark matter. In this case, you have matter on one side, and you have something that's invisible on the other side, which could be dark matter. And so we've been looking for dark matter a lot in the past few years. And we've also been trying to look at Higgs bosons in interesting ways. So here's a recent result I helped work on, where if you look at this guy, this thing on the left, this bunch of energy, this actually looks like a Higgs boson that decays to two heavy quarks known as bottom quarks. And they're all in a like kind of cone. It's a relativistic cone. And if you look at the properties of these, it turns out very likely this is a very high energy Higgs boson. But what's interesting is that actually to identify this event, we couldn't use our conventional collider techniques. We had to use deep learning. Right? This is an event we could only flag with deep learning. And deep learning is really making a big change in the way we do processing at the LHC. So with this very measurement, we've been able to actually improve the quality of this measurement significantly. So in 2016, we did a measurement, and we used, let's say, 2016 machine learning technology. So this is like CNNs, this kind of, like dense MLPs, this kind of technology. And let's say at a 50% efficiency of identifying a Higgs boson, our background rate was this value. Well, when we upgraded to the new technology, so using recursive neural nets, using some other new neural net architectures, we were able to reduce the background by a factor of 2 or 3. And with current, let's say, 20 technology, we could even reduce the background even further. Just as a note, our result actually used 2019 technology, so there's still a lot of room for improvement to reduce the background, increase the purity, and really measure the fundamental properties of the Higgs boson. Well, deep learning has really caused a lot of changes in our field, and it's leading to kind of an evolution in how we actually process the data. So what I showed you there was kind of looking at an aggregate collection of particles and trying to use deep learning to identify what these features are. But now we're starting to think about using deep learning to actually combine the detector components to make our particles, and potentially even deep learning to kind of read out the information itself. And so there's this evolution, and it's going rapidly. And just to give you an example, here's a deep learning algorithm, or at least you can go to this paper, that actually takes these different particle deposits, energy deposits, and links them and classifies the particles. And so you can get a deep learning algorithm that does this. So in the past 10 years, LHC has been running, and we made a lot of discoveries. We've discovered the Higgs boson. We've also measured fundamental properties of all the particles, let's say top quarks, W bosons, Z bosons. And we've also kind of changed the dynamic of dark matter. What we thought dark matter was 10 years ago is completely different to what we think about now. And this is largely because of the large amount of data that we've had at the LHC. What we're seeing now is an evolution towards deep learning, and an evolution towards actually looking for very small signals, or at least small bumps on tops of lots of data, because now we have so much data at the LHC, and we keep taking more. So how do we take data at the LHC? Well, this is where FPGAs make a critical role. So we take data at 320 terabits per second, and we use radiation-hard ASICs to actually do this. The collision environment at the detectors is a high radiation environment, so you need to use simple processors to read out the data. And then we send these to a large grid of FPGAs that actually do our processing. And so our first tier is FPGAs. Now, because of the high radiation environment, we only have buffers that can store an event for 10 microseconds. And that means we have 10 microseconds to decide whether an event, a collision, is interesting or not. And we only take one event in 400 and keep it to analyze it further to see if it's interesting and tells us about some new physics. The other 399 events, we just throw away in the garbage. And we have 10, just as a reminder, we have only 10 microseconds to do this, to look at the event, see if it's interesting. Well, once we do that, we actually go from our FPGA cluster to a local CPU cluster. And here we use kind of more conventional computing technology that you might be familiar with. And we have in the order of half a second to look at an event, see if it's interesting, and again, select one event in 100. And then finally, we actually once we select this event, so this 1 in 40,000 events, we can actually save this to disk and do a slow processing, and we process this on a global computing grid. So this is our full chain of processing, and it really starts from a very coarse, quick analysis of the data to finer analysis of the data to refine full information of the data. And practically what these algorithms are doing is they're just looking at the energy of the events. So we always try to keep the highest energy events, and then kind of, at each tier, we just try to select what we see are the highest energy events so that we can consistently reduce the rate going further. The problem is we know now from all of the measurements in the past 10 years that there's lots of interesting physics we're just throwing out. And there's actually potentially new discoveries for dark matter, new kinds of interactions, and they could very easily be hiding in the data that we're throwing out. And just to give you an example, here's a Higgs boson. So it's the same analysis I showed you before, a high energy Higgs boson. This one was just on the cusp of being selected. So our threshold for energy, in this case, is 450 GeV. And this one was just above that. So had it fluctuated down, right, there was some mismeasurement, we would have lost it. And for every, let's say, kind of event that fluctuates up, we tend to lose 5 or 6 or even more events that have fluctuated down. So we're really losing a lot of quality information. So how do we go from just selecting one event in 40,000 collisions to really analyzing all the information at the LHC? And that's kind of the dream of what we want to do, and kind of the motivation for this whole talk. The problem is that we're continually upgrading our system. And in fact, our 320 terabit per second data rate is going to go up and be above a petabit per second, not so long time. In fact, in about 3 or 4 years, we're going to upgrade our beam, and the data rate is going to be really incredible. So this is our offline computing. We're talking about many tens of thousands of teraflop years processing. The problem is computing hasn't helped. You are all familiar with Dennard scaling and its end. And we have to come up with clever ways to deal with our data increases, but also contend with the fact that there are limitations from computing. So are we on the threshold of not being able to take data? Well, let's take a look. So let's look at how we could upgrade our first tier, our so-called level 1 trigger. Our current technology is a bunch of FPGAs. So it looks like this. It's a bunch of racks. These are micro TCA racks. And they're interconnected with fibers. And typically between FPGAs, you're talking about 45 to 60 fibers, each running 10 gigabits per second. So you're talking about somewhere around half a terabit per second going between FPGAs. That's our kind of current technology. And we have about 100 of these interlinked to process the data. And the algorithms that we run on this are quite simple. I said most of our algorithms kind of boil down to summing up the energy. Well, you can imagine taking your detector and just taking one of the detectors. It looks like a cylinder. You can unroll the cylinder onto a rectangle. And then you have a bunch of kind of squares. So you can imagine now taking an algorithm which just looks at a grid in your rectangle and just finds the highest energy square in your grid, right? And it just scans iteratively. You can imagine taking the 10 highest energy deposits in your grid and then summing all the energy in a square around it. And that's what this algorithm does. This is actually one of our current algorithms that we run. And so it's quite simple. It was written actually in VHDL. And the nice thing is, right, on the FPGA, you can parallelize this whole scheme. And so you can run it very fast, right? We run this on the order of about, I think, 100 or 200 nanoseconds. The problem is this kind of limits our subtlety in the physics that we want, right? And so just to give you a feel for kind of the subtlety we need, well, here on the left, I have an image. And on the right, I have a slightly different image. And I won't give you time to actually find the difference. But if you look carefully, you'll see that on the right, Mona Lisa is wearing a ring. And this is the kind of subtlety we need now to really look for interesting physics. Right, here's a collision. And if you actually zoom in on this collision over into this region at the collision point, you actually see that these particles were long-lived. And finding the long-lived information is something we can do, but it's subtle, right? You can't look at the whole event and see some enormous thing, or you can't look at the event and immediately know it's a Higgs boson, right? The kind of physics that we're looking for now can be very subtle. And in fact, this is an event that could explain dark matter. It's very much a dark matter candidate. So our beam is increasing. Our system is just going to get worse because we have more collisions overlapping. Our intensity is worse. And our algorithms, we know, are not going to be, the current algorithms are just too simple. They're not going to pick up the subtlety that we need. So we need enhanced capabilities. And so we wanted to see if we could do this. We want to upgrade our system in the next few years. And so we wanted to bring ideas that we had from offline world, so the non-real-time world, where we have infinite time to process the data. We wanted to bring ideas from there to our FPGA system to see if we could run these in real time. And so one algorithm that I know very well, I came up with it, called the puppy algorithm. What it can do is it can take a set of interactions. So on the left, you have 150 overlapping proton collisions. And these are actually the ones. And what it can do is it can take these 150 overlapping interactions, reconstruct the raw inputs into particles, and then take the particles and isolate the collision you're interested in. So you can go from this busy environment to an environment like this where you have about less than 100 particles. So you're going from 3,000 raw detector inputs to less than 100 particles. And a good physicist can look at this event and actually tell you that this is a top quark pair production. You can see kind of 6 clusters of energy from jets. So we wanted to see if we could run this in our FPGA system. The problem is, well, we have 10 microseconds to make a decision. And practically speaking, with delays in fibers and other streams to process the data, we needed to do this in less than 2 microseconds with an initiation interval of 25 nanoseconds. So what did we do? Well, we upgraded our system. We added we're upgrading our system. We're going to add about 200 FPGAs into our system. And these FPGAs will allow us to do more reconstruction, so read out more of the detector, and then allow us to potentially do such an algorithm. The problem is we need to rethink the strategy of the algorithms. We can't just make a big grid and kind of iteratively scan over the grid and look for excesses. What we need to do now is do things like we do offline, right? Take a detector deposit in one detector, link it with a detector deposit in another detector, right? And eventually give you a particle, right? So how did we do this? Well, this is where HLS came in. And HLS really kind of saved the day for us, because what we needed is something where we can capture the physics. So something an algorithm a physicist can develop, but something that a physicist with a little bit of help from experienced engineer could actually deploy this quickly on an FPGA. As physicists, most of us are not very good at registered transfer level code. We prefer to write at higher level languages like C++. And so HLS was kind of the right level for us to actually process the information. But more importantly, it allowed us to develop rather complicated algorithms with very fast turnaround. And so we did it. We managed to get this algorithm to work on the FPGA. We learned a bunch of things along the line, And so to take 2 years and summarize it into one plot, here's our current algorithm. The one thing we did learn is that you had to design your algorithm to fit on specific superlogic regions, right? You couldn't, if you had an algorithm that was crossing a die, you wouldn't meet timing. So that was to say the one thing we learned. And we've actually started to deploy these in test boards. So these are actually test boards that we're going to put in our upgraded system. So you can see these pink things are the FPGAs. And you can see now we're going from, instead of 0.5 terabit per second, we have as many as 100 fibers here. They're running 25 gigabits per second per fiber. So you're talking about 2 to 2.5 terabits per second running on any individual FPGA. So we're talking about huge amounts of data. So our algorithm, well, to get it to work, we actually took our particle algorithm and we actually run it on, we take our event, split it into 6 different regions. And on each of the 6 FPGAs, we run this algorithm that makes particles. And so it does it in a region by region. And with this algorithm, we're able to actually run in 150 nanoseconds the full event reconstruction. So what did we do? Well, we took these 6 and we multiplied it by 6. And with 6 times the resources, we can run this with an initiation interval of 25 nanoseconds. So 36 FPGAs was sufficient to kind of take the detector inputs, link it, make particles. Well, the next thing we wanted to do is send these particles and actually run algorithms. And like I showed you with this Higgs boson early on, we wanted to see if we could put more advanced algorithms, things like we do offline. So we wanted to see if we could run deep neural networks. The problem is we only have a microsecond or even less to actually run this. And we need to do this with a pipeline interval that's below our collision rate, 25 nanoseconds. I mean, it's often the case you might want to run your deep learning algorithm a few times on an event. So you'll need an initiation interval that could be as many as 5 nanoseconds or practically speaking 1 clock. So how do you do this? Well, we needed to make a system that could run this fast. And so let's just look at a simple deep neural network. All right, so here's a deep neural network. We have a vector, or a neural network. It's not deep. We have a vector that comes in, has 2 inputs. And to get an output from this neural network, we need to multiply it by weights, add a constant, right? We do a vector addition, and then apply an activation function on this. And that gives us our output. To do this, so that you can have a pipeline interval of 1 clock, what you want to do is take the multiplier and then do all the multiplications at once, send it, and then do the additions, right, in 1 clock, and then do the activation function with a lookup table in 1 clock. And the nice thing about this scheme is that you can continue to send a new vector of inputs every clock, right? So effectively what you're doing is you're unrolling the neural network onto the FPGA fabric. Well, you can scale this up to a neural network. And here's a neural network that actually can identify Higgs bosons from collections of particles, as well as top quarks and W and Z bosons. It's a small network by industry standards, right? It only has 4,000 weights. But this network we can run with an initiation interval of 1 clock. And we can fit this actually on an FPGA. The latency for this whole network is actually 75 nanoseconds. So it's 15 clocks at 200 megahertz. Well, how did we get this algorithm to fit? We need to use all the standard tools you're probably all familiar with. So we pruned our algorithm, we quantized our algorithm, and we also have a tunable parameter that allows us to kind of dial up and down the amount of DSPs that we use in our algorithm. So I won't go into too much detail, but suffice it to say that actually zero suppressing our algorithm was relatively easy in HLS. And when everything's on the fabric, a lot of the zero multiplications can be compiled away. Our bit precision, we found that, kind of consistently, we find that 12 to 13 bits is sufficient for the physics algorithms we're interested in. Now, just to talk about reuse factor a little more. So what this is when we developed our neural networks, we wanted to make sure our tool was flexible so that we could change the sizes of the algorithms on the FPGA. Because it's likely we're not just going to have one neural network on an FPGA. We're going to have many neural networks running on our FPGA. One doing Higgs boson identification, one doing tau lepton identification, one doing muon identification. There's all sorts of different particles, and each has a kind of different strategy to reconstruct it. And so we wanted to kind of dial up and down. So we had something we call reuse factor, which is effectively just a tunable parameter for your initiation interval. So if you want to, let's say, have one DSP, do 6 multiplications, you can set your reuse factor to 6. And this will, you'll then have an initiation interval of 6 clocks, but you'll have 1/6 times the amount of DSPs that you would have in your initiation interval of 1 clock. So here's our results for our very simple network that we showed you before. The latency with a reuse factor of 1, so initiation interval of 1 clock, is about 15 clocks. And it gets worse as you go to larger reuse. And your initiation interval also gets worse. It goes by this reuse factor. But you can see on the right here, your DSPs. Well, once we pruned our model, it fits into a single FPGA nicely. And then when we go to use our reuse factor, we can reduce the DSPs by 2, 3, 4, etc. Well, this is, let's say, a first study that showed we could run neural networks in the latency and initiation intervals that we needed. But there's a lot of algorithms, right, that we'd want to do. And so we made a tool, a generic tool that physicists and anybody can run, and we call this HLS from Mel. And what this does is it will take a conventional neural network and then convert it to HLS code. We have it working on Vitis, Intel, Mentor Catapult. Although in our official release, I think we only have Vitis HLS at the moment. And then this will, once you run your HLS, you can do your tuning, and then you can output a kernel that you can put in your system. We've gone all the way to running these in our trigger system, actually. I won't talk about kind of the features, but you can do lots of different neural network architectures, and we're constantly adding more, including kind of old style like boosted decision trees. But the kind of bigger thing I want to say is that this is a different paradigm to most deep learning approaches. So if you look at kind of original or traditional deep learning approaches, you'll see that like the Xilinx ML suite, what they'll do is they'll use a big flexible layer. So you have a big systolic array, and you have lots of you have some features so that your layer can actually do all sorts of different processing. Right, you can do different styles of CNNs, dense layers, etc. And you can take your inputs and just run it through this big flexible layer. Well, this is great for very large models at longer latencies, like millisecond timescales. But if you need nanosecond timescales with nanosecond initiation intervals, you need to take your network and kind of unroll it onto the fabric layer by layer. And so you make a dedicated firmware for each neural network. And that's what we do. This is the HLS from Mel paradigm. So this is good for very small models and good for ultra low latency. And it can allow you for high throughput, but it doesn't necessarily allow you to run large models. And so being able to run large models is, to say, more advantageous if you use these kind of big flexible layer approaches. So what's happened to HLS from Mel? So inside physics is becoming a standard tool. And I can show you a number of applications. It's going to be in the next running of LHC, and actually several algorithms. Both the big collaborations, LHC and CMS, are using it. And what we're seeing, with our upgraded system is we can get like 2 to 5 times more Higgs bosons with the same data rates, right? So that means you're increasing your sensitivity by factors of 2 or 5, which is really transformative, right? It changes the quality of physics that you can do. So what about running at longer latencies? So let's, instead of looking at running things really fast, really quickly, let's try and take a longer look and see what we can do. And we can look at our existing tiers, and these are both CPU-based. So we wanted to see if we could augment these with FPGAs. Our current system, we're just going to focus on this middle tier. It's about 35,000 CPU cores, and you have about half a second to run an event. It takes data in at a rate of 100 kilohertz, but if we could do more, it would be great. The dream is actually to get to megahertz. This is kind of our internal goal. And there's been discussions about how to do this potentially with GPUs. So we wanted to see if we could do things with FPGAs. And so this brought us to the cloud, where we could get heterogeneous systems now, right? And so here's a first study we did with Microsoft with the Azure machine learning stack, so using the brainwave FPGAs. And so what we did was, well, they had existing neural networks that they run in their system. So in this case, it was ResNet 50. So we retrained a physics problem. We identified top quarks. So a boosted high energy top quark will give you a kind of average energy distribution like this. Whereas a background, a quark or a gluon will give you an energy distribution like this. And so you can make a network on these jet images. And in fact, ResNet 50 is a pretty good architecture for this. We were able to make comparable to the world leading top tagger. And so we wanted to see how fast this would speed up our system. And these are the results that we got. It was quite transformative, right? ResNet 50 on our existing CPUs that we use for our clusters takes about between 1 and 2 seconds. On the FPGA, it took about 1,000 times faster, right? And this is a kind of batch one, arbitrary batch processing. With GPUs, the current GPUs at the time, we eventually were able to approach the FPGA rates. But in fact, the FPGA, in this sense, was faster. But 1,000 times is a huge number. So we realized that we had to kind of rethink how we're going to process things. right? So we can't just take our CPU cores and, let's say add FPGA cores. We need to have an FPGA or a GPU serve many of these processors, because if it's 1,000 times faster, you really get a huge advantage. The caveat, of course, is the accelerator here is just running one algorithm, and at the LHC we have, I'd say, on the order of about 20 core algorithms that we need to do for each collision, right? So there's 20 different algorithms that we need to run. And so we'll need you can imagine 20 different, let's say, FPGA servers, each running a different algorithm. And so we wanted to see if we could build this paradigm, right? So you can imagine having an event, right? You have an input, you run an algorithm, you have an output, and now you want to add a coprocessor. So you can add an FPGA here, and you run your algorithm really fast there. You can do now you have some time on your CPU, so you can actually do an asynchronous scheduling of your software. And so this is what we did. And you can now run, let's say, multiple events at the same time, as long as you deal with the bookkeeping of running multiple events. It turns out our asynchronous scheduler is quite good. But what this means is that we can wait actually quite a while for things to process. So you could imagine if you don't have GPUs locally, you could send these things to the cloud and then have them come back. The unfortunate thing about this is it also means that slower latency processing, all right, I don't know if I would say unfortunate, but slower latency processing, like you would get on a GPU, is actually amenable to this, right? Because often the case of GPU, it'll take you a while to get a lot of inferences from you. But in light of this, we wanted to test these things. So we made our system to this asynchronous scheduler. We call it Sonic. That allows us to do calls to our remote servers. And then we made a bunch of remote servers. So we made an FPGA server infrastructure we call FAST. And we've integrated this with the Xilinx ML suite and HLS from ML and so on. And the nice thing is we use the same protocol as the GPU tool, the NVIDIA Triton Inference Server. So you can kind of seamlessly swap between the two. And so we did a case study. We took a very simple algorithm. So it's a simple neural network. And what it does is it reconstructs the individual channels, the energy of the individual channels of one of these calorimeters here, the Hadron Calorimeter. And it's actually a little bit better, our algorithm. And what we see is that for the 16,000 channels, if we run this on a GPU, it takes about 2 milliseconds. On an FPGA, we use HLS for ML, and we actually unroll the whole algorithm onto a single superlogic region. We can actually run this at let's say 100 microseconds for all 16,000 channels. So this is a kind of very efficient use of resources. And you can see it's 20 times faster than the GPU, but more importantly, it's 600 times faster than our nominal algorithm that we're currently running. So we wanted to see if we could integrate this. And so we did a test. So here's a test with GPUs. So what we're doing is we're looking at the total time to process information. And we're doing this we're scanning the number of CPU cores that we have. And we're sending this, in the case of the red here, to one GPU. And so what we see is that we can reduce the total time of our total processing by 10%. Kind of the maximum for this one algorithm is 11%, right? We have other algorithms that we're running. So this is the total time of processing, not just for this algorithm. And so you see that, let's say, beyond 300 simultaneous processings, we start to actually get slower with the GPU. Now, with the FPGA, what we saw in AWS is that with about 1,500 simultaneous processings and one FPGA, we're able to speed up our intermediate tier of computing by 10%. And interestingly enough, actually, the limitation here was not the FPGA. It was actually AWS. They have a network cap at 25 gigabits per second. So if you get rid of this network cap, you can actually get up to 550 simultaneous CPUs serving by one GPU or one FPGA. So what does that mean? Well, it means that a 30,000 core system, like this system, can be reduced by 10%. So we can reduce, let's say, 3,500 CPU cores with 6 FPGAs. Right. So this is a large reduction and kind of an idea, a scheme, a glimpse of what we could do in the future. We've tested other algorithms. We find that the small algorithms are fast on the FPGAs, and then the large algorithms are kind of comparable on FPGAs and GPUs. It depends on the details. But what we see is that there's really kind of a scheme for heterogeneous computing in our intermediate tiers and our larger tiers. And it's something we're quite excited about. And it's something that might actually solve some of these computing limitations that we have downstream. There's kind of a trade-off between whether a GPU or an FPGA is better. But we're open. What we observe now is that there's maybe a best solution depending on the processor. Okay, so now I want to kind of expand these concepts. So what we've done now is we've taken our current system, we've upgraded the FPGAs at our first tier, and we've added FPGAs to our second and our third tiers. But let's zoom in on this intermediate tier. What if we were to kind of change the dynamic completely? And instead of just kind of running this tier on its own and just connecting it to this first tier, what if we just rotate this guy by 90 degrees? And we actually have the FPGAs connected to our FPGA accelerators, and then have these talk to our existing CPU cluster. Well, effectively, what we could do then is we could throttle our data rates, right? Our original data rates at the collision rate of 40 megahertz, our computing tiers at 100 kilohertz. You can imagine a tiered system, right, where you throttle between 100 kilohertz and 40 megahertz. And in fact, there is a prototype system that does this. You can ask me offline about why we have it. But this led us to a development that we've been working on recently called Aegean. And so the idea here with Aegean is to take an existing software stack called Galapagos, where Galapagos actually connects. It's a kind of a full stack to connect FPGAs with FPGAs and CPUs and everything else through network. And we wanted to combine this with our HLS for ML, where we have very fast inference times for small neural networks. And just a point is that Aegean and Galapagos are both archipelagos. And the idea here is that you want to connect a bunch of disparate processors so that they can all act as one. Right, so that's the idea. So we started with the Galapagos stack. This is the heterogeneous stack that allows you to go from physical hardware to communication. And this can be connected to CPUs. It can be potentially connected to other devices. So there's lots of flexibility here. And we added HLS for ML inside of it by building Galapagos bridges and then interconnecting and then we interconnected our we built FPGAs by making a Galapagos bridge layer. So we'll have some neural network layers on a single FPGA, and then we'll connect it to another FPGA. We'll have, let's say, the further neural network layers, and then you can connect them all together to have one large neural network. And the nice thing is, between the different FPGAs, with the Galapagos protocol, we can get 100 gigabits per second. So the idea here is that you can make a neural network that runs really fast. So under this HLS for ML paradigm of unrolling the network onto many FPGAs. But now with Galapagos, you can interconnect it. And so you get Aegean, a full framework to actually deploy neural networks on a distributed set of FPGAs. And so here's our flow. It's very much like HLS for ML. You can start with a neural network, and then you can push a bunch of buttons, tune your HLS, partition this, and then actually we have automated tools that will spread the different layers across a GPU and a CPU and FPGA cluster, allowing us to run neural networks across many processors. So we did a test of this. So we took an anomaly detection algorithm. So this is an anomaly detection algorithm that can look at an event and identify whether there's a physics anomaly or not. It can look at Higgs boson anomalies, top quark anomalies, these kinds of things. And we were able to unroll it onto 3 FPGAs. And our pipeline interval is, with this algorithm, is 2.8 microseconds. And we can run this algorithm in 80 microseconds across all 3 FPGAs. Now, this algorithm is actually it's quite large. It's much larger than our typical HLS for ML algorithms. It's about 500,000 weights, right? And kind of the algorithms we've been looking at, for our first tier of FPGAs are about a few thousand weights, right? So less than 10,000. If you compare this to just a single FPGA implementation, the actual single FPGA implementation is actually worse than 3 times the latency. So it's the latency of a single FPGA is 260 microseconds. And then you also have to deal with the fact that the initiation interval here, it's in principle 5.6 microseconds, but you also have to deal with the fact that you have to send things back and forth across the FPGA. So it's going to be actually worse than this. So really, kind of this Aegean flow allows us to kind of do very fast networks and allow us to run things very like to effectively throttle between 40 megahertz and 100 kilohertz. Right, 2.8 microseconds, right, just as a note, is getting close to a megahertz, right, in terms of processing. So we wanted to see how far we could scale this. And so we've done this now with ResNet 50. And we actually can split it on 9 small ZU19 FPGAs. And just as a scale for resources, right, if you actually just take the bare resources, you could actually fit this on 2 Alveo U250 boards. And the nice thing is that the throughput on this system is actually 1.5 milliseconds. So we wanted to target something similar to what we had with the brainwave. And so we can, with our system, we can get to similar throughputs, but now distributed across many FPGAs. Now, the nice thing is that it's just a matter of tuning our reuse factor to make this run even faster, right? We'll have to use more FPGAs, but you can envision running things very, very fast here. So I've kind of given you an idea of how we're thinking about integrating this into the LHC. This is just a first development, so it's a first idea of how it works. Again, we're running a single inference at a time. We're pipelining it. We go image by image through this algorithm, or event by event. And this is really a natural way to link CPUs and FPGAs. So I'm hoping this will change kind of the paradigm of LHC data acquisition. But there's really lots of room to explore. So in the last kind of last part of this talk, I'd like to just highlight a few exciting things that are going on in the fast machine learning collaboration. So I'm part of a fast machine learning collaboration. You can go to our website, fastmachinelearning.org, and you can see here's our first collaboration meeting. In fact, we just had a meeting recently where we had order 500 registrants. So there are a lot of excited parties. And the collaboration, I'd say, is now more than 40 active members at 10 institutes. We have a weekly meeting. And our goal here is to bring these ideas of accelerated machine learning to science. And so let me just highlight a few examples where some exciting examples where really FPGAs are playing a leading role. So one thing is controlling accelerators. So if you have a beam of particles and it's going around an accelerator, this is the Fermilab complex, and you want to actually kind of keep your beam controlled, what you'll need to do is to say measure the beam profile, and you can measure this with the sensor, and then adjust the magnets so that your beam remains tight. It remains like a tight circle, and it goes and continues to be circulated through the beam. Well, the thing about this is that kind of deviations in the beam, fluctuations, can happen on the scale of 1 revolution around this accelerator. And if you just calculate the time it takes to go around the accelerator, it's about 10 microseconds. So what you need is an algorithm that can, let's say, read the sensors, process the information, and actually adjust the magnets to counter any kind of anomalous variation of your beam. If you don't have this, your beam will, in some cases, it can blow up. It can cause damage. But more importantly, you want to keep your beam nice and focused so that when you fire it on another beam or on a target, you can actually get high data rates. So here's the actual algorithm. We have a first prototype algorithm. We run it on an ARIA 10. And you can see we can actually run this algorithm in 2.7 microseconds. So here's the first idea of something we're working on. Another thing that we're working on is electron microscopy. So you can imagine taking an electron microscope and then kind of scanning materials. And you might want to scan various different materials. So these are different materials of, I'm not a material scientist, so it's like leads, I don't want to say. But you can imagine scanning this guy. And sometimes in the middle of your experiment, something might be wrong. So maybe some material's destroyed or something's off. And you want to adjust your experiment, either adjust the sensors, stop the experiment, do something. The problem is to actually make this image at the moment, you go pixel by pixel. You have to actually you need to find the resonant frequency at each pixel. And this requires some algorithm that takes some time. And then you want to actually, once you get the information about this pixel, you want to send this back to your scope so that you can either adjust the parameters or determine if your measurement is just not correct. Redesign your experiment on the fly. Well, the data rates we're talking about from these scopes is quite large, and you want to be able to kind of do these adjustments in less than a millisecond. So this is again a case where really only FPGAs could do this, and we already have neural networks that can actually do a process a pixel readout at a time, and it's an active area of research to see if we can actually do real-time optimization of electron microscopy. So to pick another physics example, another thing we're excited about is neutrino physics. So you may be familiar with the proto-Dune experiment. Or you might be familiar with the Dune experiment. This is going to be a large neutrino detector that's running in the US. It's going to start running kind of in the mid to end of the 2020s. And there's already a small experiment called the proto-Dune experiment. This is what it looks like. It's a big vat filled with liquid argon. And what you do is you take photos of the liquid argon to look for particles. I'll show an image in a sec. The important thing about,
Phil, just a quick note, you're down to less than 9 minutes here.
Okay, I'm almost done. So just as a note, kind of the interesting thing about reading out this detector and reading out neutrinos is that you're very sensitive to supernova. So 99% of the energy from a supernova actually is released from neutrinos. And so if you want to really understand supernova, you actually want to look at neutrino detectors. The problem is that neutrino detector supernova signatures are quite faint. So just to give you an idea, this would be kind of the scale of a supernova signature. So this is an image of your neutrino detector, of the liquid argon neutrino detector. And this is, let's say, 7 centimeters. So to put in scale, you have this giant volume, right? And you need to take all of these images. And you want to look for a signature that looks like this little blip. Well, the thing is, you need to do this. The signatures only live for about 10 microseconds. So you need to do this at a rate of 100 kilohertz. Right, so if you want to actually look for supernova, you need to be able to process this real time with a system that's actually quite similar to the Large Hadron Collider system. So this is another interesting problem. And we've already done kind of preliminary work. And we've seen that machine learning, let's say, on GPUs could speed up our processing by a factor of 20. But this is not real time. The real time system, we could only envision with FPGAs. And we suspect there are even potentially larger improvements there. And so finally, I'll just talk about kind of a rapidly growing field called multi-messenger astronomy, which is, in addition to, let's say, finding supernova with neutrino detectors, you can imagine finding supernova with other detectors, so telescopes or a gravitational wave detector. And you can imagine doing this all together. It's often the case that gravitational waves from a supernova come first, and then you get the neutrinos, and then you get the light signatures. So you might want to find the gravitational waves first, send it to the neutrinos, send it to the telescopes, and then be able to do synchronous measurements. And this doesn't just apply to supernova. It can apply to other things like compact binary mergers, kilonova, gamma ray bursts, and so on. And so here's here's at least what a gravitational wave signature looks like. So you get kind of a wiggle, so this frequency wiggle. And it will wiggle for about, let's say, a fraction of a second. And so the idea is you need to find this wiggle over the noise. And actually, if you have multiple detectors, you can kind of synchronize the wiggles and get a vector for where the source came. And so you want to be able to do this basically in real time as the signal comes. So this is an active area of research. And we're just starting to develop deep learning algorithms now that can actually denoise our detector and actually find these wiggle information. But this is just kind of the beginning with the gravitational waves. There's an arsenal of telescopes that could imagine also doing this and sending this to some large giant system, and effectively turn all of these into one giant, let's say, telescope-like system to look at supernova and look at all these astrophysical phenomena. So in summary, there's a lot of different exciting science experiments that are dealing with very large data rates and real-time data rates. As part of this, FPGAs are really playing a leading role in many cases. Deep learning is also playing a leading role. And I have to say that HLS has been transformative for people in my field and starting to be for others, because it allows us to really take complex algorithms and deploy them quickly to really improve the quality of science. So just in summary, thanks to all of these people, and then thanks also to the FastML collaboration. Okay, thank you.
All right, thanks a lot, Phil. A lot of exciting stuff. So not a lot of time. We'll take some questions and just remind people that a button will show up, I think, on the bottom right that you can follow Phil into a discussion room. So I'll start some of the questions here in the chat. Can you highlight the differences between HLS for ML and FIN? What made is valuable to build a different tool building similar architectures?
Yeah, so that's kind of a long question, but I would say HLS and FIN are actually quite similar. So we actually started HLS for ML 2017. So I think it was around the same time that the FIN was being developed. At the time, FIN was very focused on binary networks. And also we were, as physicists, we're not aware of it. So we wrote our own framework to do this. There is a large overlap with kind of the FIN style design. I would say FIN is much more effective for larger networks. And it wasn't really designed for kind of LHC data rates. But I'd say there's a lot of things that we're learning between the two. We actively collaborate with the FIN team. And I'll leave it at that. But it's something that we've learned a lot from FIN, and we're continuing to learn from them. We talk to them quite regularly.
Okay, here's a long question. This question is specifically about the use of ML for data analysis at CERN for new searches like search for supersymmetry. As we all know, ML requires a lengthy process of training the ML engine. Such training uses millions of pieces of data presented to the ML engine so that the engine can recognize a similar event in the future. So do you do the ML training by simulated events, since you don't have any real ones yet, or do you do training in some other way, which would be much preferable because simulated events depend on the details of the theoretical models of supersymmetry? Does this sound like another chicken and egg problem for future searches at CERN using ML?
Yeah, so this is a question that's an active area of research. So for most things, we actually build simulation for this. So imagine you have a supersymmetric stop quark pair production, some complicated thing. What we do is we make simulation of this, and we train our neural networks with the simulation. One thing I should say is our simulation is incredibly good, right? Like for processes we do know, like the Higgs boson, it's like almost spot on, and we have lots of it. So it's easy to kind of build deep learning algorithms. For new physics processes, the strategy has traditionally been to just write down all of the possible signatures we can think about, and this is like thousands, and just search for them iteratively, one by one. There are ideas now to kind of get rid of the signature and look for kind of what we call anomalous decays. And there's a rich literature actually that's like blossoming about anomaly detection, where you actually don't insert a signal, or you insert a collection of signals and you can interpolate between the signal. I don't have time to talk about this, but I'm happy. If you want me to give a seminar on this, I just wrote a bunch of papers on this.
All right, here, let's see if we can squeeze one more in.
There are 45 seconds left. I wanted to step in and say thank you so much for giving a fascinating talk. It's a relief to have somebody come to this conference and tell us in the same talk that HLS works and that FPGAs are working for him better than GPUs in many cases, with some credible analysis to back up that claim. So thank you very much.
Yeah, thank you.
And I hope that you will follow us to the breakout room. I don't know what the capacity of the breakout room we might find out. And well, we're gone.
I thought we had 13. We have 9 seconds. So,
well, maybe not. So there's going to be a button, Philip, for you to actively